With this video, we shall demonstrate how optimization is used in Matlab Simulink environment. We shall use main optimization Matlab file. We shall use one Matlab function which defines criterion function, and we shall use the Simulink scheme. These files are also open. This is the main optimization program. This is the function which realizes the criterion function, and this is of course the Simulink scheme. In this scheme we can notice the main PID controller, this is the auxiliary controller, this is the plant, and this is the criterion function realization. The auxiliary loop is inactive because this parameter is set to 0. The auxiliary controller KPP equals 1, so that we shall really optimize only the parameters of the PID controller KP, TI, and TD. These are proportional gain, integral time constant, and derivative time constant. For the optimization, we use integral time average error. This is integral from 0 to 100 t multiplied by absolute value of the error. T is of course the independent variable, and this is implemented with this yellow part. Here we obtain the absolute value of the error. We multiply it with the clock signal, what means this part, and then we integrate this product, and the result is shown with this display unit, but it is also put to the scope block and to the output block. This is fourth output of this scheme. With this main program for optimization, we at the beginning clear the workspace, we close all windows, and we define some constants to be global. This means that all these constants can be used with all program modules. We define final simulation time. We select the main loop to be active and auxiliary loop to be inactive. We define the gain of auxiliary controller, and we define that the reference signal is 1 and the disturbance is 0. So we shall optimize the control system in the presence of the reference signal. Then we define the initial values of the PID controller. These are values which were obtained previously with Ziegler-Nichols reaction curve method. With these parameters, we start the simulation of our Simulink scheme. I can also select this part of the program, and pressing F9, I execute this part. I can show the output, which is shown in this scope block. We can see the step response to the unit reference signal of this control system using initial values of PID controller parameters which were obtained with Ziegler-Nichols reaction curve method. We can notice that the overshoot is approximately a little bit more than 50%. With this row, some options for optimization are defined. We define 50 iterations, but the optimization can stop also if the criterion function or if parameter changes are very small. If they are smaller than 0.01. This pair means that during optimization we shall obtain some values. So then the optimization is started with this Matlab row. So we are calling fminSearch function. We define the name of the file with criterion function. We define initial values of PID controller, and we define the options which were actually defined in the previous row. And optimization calculates the optimal values of parameters and the minimal value of criterion function. And this is actually the part with the criterion function definition. At the beginning, we define constants as global constants. This is the same row as in the main Matlab file. And of course, these parameters here are linked with these parameters in the main program. That means KPTI and TD have here some initial values, and with these three commands, these parameters are transferred into KP, TI, and TD so that the Simulink scheme has proper values of parameters. With these rows, we define some options. These are options in connections with workspace. This can be used as a kind of template. I will not comment the details. And then the most important thing is to simulate the system. The system is simulated from 0 to the final time. And of course, we define the options. And the sim function returns three vectors or matrices. Independent variable, this is the matrix of states, and this is the matrix of outputs. And outputs are defined in this scheme with output blocks. The final stage of this function is the calculation of the criterion function, which is actually the final value of this signal here in the scheme. We obtain this final value so that we calculate the size of the matrix X. NT and NX are sizes of this matrix. And NT actually means how many time points were realized during simulation. If we execute this row, f equals y and t4, this means that we addressed the fourth output, and we also addressed the last value of this matrix. Optimization is performed by selecting these two rows. Now I press F9, and in the command window I can observe the result of the optimization procedure. Now the optimization stopped. I will go back to the beginning of these results. The results are presented in 4 columns. In the first column, this is the number of iterations. Second column, the number of criteria evaluations. And the third column is the value of the criterion function. At the beginning, the value was approximately 390. Then I will go to the bottom of these results. I can notice that we obtained 50 iterations. In these 50 iterations, we had 87 calls of the criterion function or 87 criterion function evaluations, and the final value of the criterion function is approximately 52. We can also notice the optimal values of parameters. This is the parameter of P controller, I controller, and D controller, and this is the final value of the criterion function. In the final part of the program, we transfer optimal values of parameters obtained by optimization into controller parameters Kp, Ti, and Td, and we perform with this row the simulation with optimal parameters. Here we plot the response of the situation with initial values of PID controller parameters and with optimal values of controller parameters. Now I will select this part of the program. I will press F9, and these are final results. These are results of the control system response with initial values of PID controller parameters, and this is the response with optimal values. We can notice, of course, the big difference between two responses. It is also interesting to observe dynamically the criterion function. I will open this window, and this is the response of the criterion function. Actually, this is the output of this integrator, and we can see from this main window that the minimal value of criterion function is 52, and this is this value in the ending part of the response. But if we want to dynamically observe this the course of the criterion function, we select these two rows. I press F9, and we can see how this curve is changing. We can also see that we do not actually obtain in each iteration the improved values of parameters, but in most cases it happened. Now the optimization is finished and we obtain the minimal value of this criterion function. We can also observe the process output during optimization. I will open this scope block. We can see here the optimal response, because this is the course of the level with optimal PID controller parameters. But if I want to execute optimization, I select again these two rows, press F9, and this is actually the dynamical presentation of how these transient responses are changing and approaching to the optimal response. This optimal response has just appeared. So this was the optimization in the presence of reference signal. But if we want so-called disturbance rejection mode elimination, that means that the control system is in the presence of disturbance, we must put the reference signal to 0 and the disturbance signal to 0.5. Let's go to the program. So I will put the reference signal to 0 and the disturbance signal to 0.5, and this is everything what is needed actually to start the new optimization procedure. I run this program, and now the optimization is just performing. Okay, again, to go back to these results, the starting value of the criterion function was 104 and the optimal value was 12. And these are optimal values of the parameters of PID controller, and it's well known that the controller parameters are different for so-called reference tracking mode and for disturbance rejection mode. And this is also the final or minimal value of the criterion function. And these are the results of the disturbance rejection mode. The blue curve is the curve with initial values of parameters, which were, as we know, obtained with Ziegler-Nichols tuning rules, but the red curve is the curve when we used the parameters with computer optimization. And of course, again, the big difference can be noticed.